Today we're going to talk about formal charge and resonance. So let's start with formal charge here. Formal charge is the charge a specific atom is responsible for in a molecule. And this definition might be a little bit different than what you're used to seeing for formal charge, but this is definitely how I think about it. I think about the responsibility of the atom in comparison to its valence shell electrons. And so let me show you what I mean. Let's talk about ammonium, NH4. And how is ammonium drawn? Easy, we know this. But remember, ammonium is a polyatomic ion, so it has a positive charge on it, a +1 charge. And what we're trying to figure out with formal charge here is which molecule, or which atom, I keep saying molecule, which atom here in ammonium is responsible for that positive charge. And so this is going to have us think back to our common bonding patterns. That was in our last video. And if you remember, nitrogen in its neutral state likes to have 3 bonds and 1 lone pair. And what happens when you take away one of those electrons is that this becomes a 4th bond. And so when you take away an electron, you have more protons than electrons balancing it out. So therefore, this nitrogen is positive. And that's why we can say this nitrogen over here is positive as well. And this positive charge on the polyatomic ion comes from nitrogen. So let's officially give kind of a way to figure this out for everything. Now, the way that I like to figure out formal charge is by saying it's equal to the number of valence electrons an element normally has. So I'm talking about on the periodic table, not in the specific element in this molecule itself. And then I like to do minus electrons assigned. Now, what the heck does that mean? That sounds a little confusing, right? What I mean by that is it's half of the bonds that it creates. And because remember, it's only contributing to half of that bond. Half of those electrons in those bonds come from the other element. And then I'm also talking about all lone electrons on it. So when we look at NH4, let's do our formal charge of nitrogen. So it's equal to the number of valence electrons that nitrogen normally has, which is 5, and then minus the electrons it has assigned to it. So we can count those here. It's 1, 2, 3, 4. It's only contributing 1 electron to those bonds, and so those are the ones that it is responsible for bringing to the table. So minus 4 electrons. So we can see that the formal charge is positive 1, right? Now let's do another one here. And we're going to go ahead and do something called, I always get this wrong, it's called tetrafluoroborate. So tetra, 4 fluorines on a boron, and this has an overall negative charge. So we could write that as BF4 negative. So let's remember our common bonding patterns here. We know fluorine is a halogen, so it's going to want to have 6 electrons outside of it and 3 lone pairs and 1 bond. And we can definitely do that, right? So all of these fluorines are neutral. But this boron, this is what's contributing to our negative charge here. Because if you remember, boron's common bonding pattern is just 3 bonds. It's an exception. It's only going to have 3 bonds. So when we add 1 more electron and allow for this 4th bonding capacity, we have more electrons than protons now in this boron element, boron atom. And so this is going to be negatively charged. So we can say boron here is negatively charged. And we can see this when we do our formal charge of boron here. So it's equal to the number of valence electrons boron normally has, which is 3, minus how many valence electrons we have assigned here, how many electrons it's responsible for. We can see that's 1, 2, 3, 4, because we only take half of those bonds. So when we do 3 minus 4, simple math, we have -1. And that's why this boron here has a negative charge. So let's go ahead and talk about a more complicated example. And that's going to be methyl nitrite. I'm going to write that out for us here, methyl nitrite. And methyl nitrite is organized like this. Now, I haven't filled in all of our electrons yet. So let's use our common bonding patterns to figure out how we want to do that. So really, we know carbon is set. Carbon usually has 4 bonds. So that's all good. We know our hydrogens are set. They normally have 1 bond. All good. Now what about our oxygens? Oxygens normally have 2 bonds and 2 lone pairs. So we need to figure those out. And also nitrogen. Nitrogen normally has 3 bonds and 1 lone pair. So another one that we need to figure out here. So let's start over here with this ending oxygen. And let's throw in another bond. So that means oxygen is going to have 2 bonds. Throw in its lone pairs, and we're done with that. Now nitrogen, coincidentally, has its 3 bonds it's supposed to have. We can just throw in a lone pair here. And then oxygen is supposed to have 2 bonds and 2 lone pairs. Boom. So let's check out the formal charge of our oxygens. Let's do oxygen number 1 first. We're going to call this one number 1. We're going to go over here and say, oh, number 1. So its formal charge is equal to the number of valence electrons it normally has, which is 6, minus how many it has assigned here, which is 1, 2, 3, 4, 5, 6. 6 minus 6 equals 0. So we're in business there. We don't want charges on these because this is a neutral atom. We're not being, or not a neutral atom, a neutral molecule. We're not being given a charge, so we don't want things to have a charge. And this is oxygen number 2. So oxygen number 2, its formal charge is equal to 6 minus how many it is responsible for here, 1, 2, 3, 4, 5, 6. All right, so that means we have a formal charge of 0 on both of these oxygens, which is fantastic. But now let's talk about resonance. So I'm going to just fit this down here for a minute. Resonance. And resonance is really kind of the different structures that can be shown for different molecules, the different structures that can appear. Because, you know, we easily put in these electrons to make it neutral, right? But there are other ways that these electrons can fill into methyl nitrate. And they will happen in nature. You know, these other ways that aren't as idealistically charged are going to happen in nature. So let's talk about this again, and let's show another version of methyl nitrate. So instead of having the double bond here, like we put it, we could put it here. And this nitrogen is still satisfied, right? But what happens now? Oxygen has 3 bonds, and we're still going to put a lone pair in. But this means that this oxygen is positively charged. We've taken away one of its electrons. This is carrying a positive charge here. And now, when we fulfill our octet for this oxygen, we're going to put in 6 lone electrons, 3 lone pairs. And if you check this out, this oxygen is negatively charged based on our common bonding patterns. So now we have charges going on. And we don't want charges going on. You know, this is a neutral atom. But if you do look, these charges do balance themselves out. One positive and one negative, they do balance out. But this is bad. This is called charge separation. It's when a charge is spread across a molecule. We have opposite charges across a molecule. We don't like charge separation. We ideally do not want charge separation. But realistically, is this a way that this molecule can show up in nature? Yes. And is this up here another way it can show up in nature? Yes. So both of these happen, and these are called resonance structures. They're the different kinds of structures that these molecules can show up in nature. So then we're tasked with the job of finding out which one is better. Which one is better? And so, there's kind of an easy way to do it. We look at this one up here, our first one, and we see that it has no charges on it. We see that it has octets. We see that it's stable, and so we can pretty much assume that this one is going to be the better one. And we also look down here at our second one, and we see there are charges. The charges are spread across the molecule. It's not as stable. It's not as low energy. So we're going to think this one is not really the most prevalent in nature. Most likely, the stable form is going to be more prevalent. But in reality, what we see is called a resonance hybrid. And so resonance hybrids, we can best describe them, let's say, using an ozone molecule. Ozone is O3, right? So ozone, we can either do this. We can have 2 bonds here, 2 lone pairs on this oxygen, and then 1 bond here, and 3 lone pairs on this oxygen. Because oxygen here cannot have 4 bonds. It just can't. It's not in the capacity of oxygen. So this oxygen is going to have a positive charge, and this oxygen is going to have a negative charge. But what we can also see is that we can flip around these bonds. So this oxygen might have the double bond, and this oxygen might have the 3 lone pairs. So in reality, these are changing. We actually see the negative charge over here and the positive charge still on here. And both of these are the same, right? They don't have any better option. There's no option with no charge here. So what we see in nature is called a resonance hybrid. And that resonance hybrid is going to look a little bit like both of these. What it's actually going to have is a bond and a half in between these oxygens. 2 lone pairs here. And then that third lone pair is going to kind of float. It's going to be where it is. So this is going to be our resonance hybrid. And we see this as what is in nature. And this is kind of that combination of the 2 options here. And before we move on, I do want to correct myself too. There is no third lone pair that floats. It is tied up in these half bonds here. So that's kind of a lot of information for today for this video. We talked about resonance, we talked about formal charge, and we talked about kind of how to figure this out and how to figure out what might be the better option. We're going to go into this in more detail in a later video, and my name is Ben. Thanks for watching.